Hello, back again. Guess who's back? Back again. Hindo's back, Hindo's back, Hindo's back, Hindo's back. Tell a friend. All right, so let's get on here and do a problem. So this is Unit 11, Problem 9, okay, electric field. So this one's actually much easier than the last one, Problem 6. So problem 6, I think, is the hardest one in the whole unit. And this one is much easier. It's just the way the force diagrams work out for us. So the electric field being in a perfectly x direction helps. So what do we have? We have our free body diagram right here. We have, this is FG. FG. Okay, we have FT coming up this way. And we have FE, we'll draw in blue. And the force due to a charged particle in an electric field, we'll call this FE. Okay, so I'm going to redraw this right here. Well, I'll redraw it here as I do it with some small modifications. So FE, well, FE is equal to EQ. So the force due to the charge in the electric field is just the product of the two. So for us, E is, redid directions, Brandon. And so it's E, and our E is not known. That's what the question is asking for. But we do know Q. Q is down here, and it's 35.6 microcoulombs. Not micro, sorry, so get rid of that one. That stands for microcoulombs, which is 10 to the minus 6. So all you have to do is 35.6, and then to convert it, you just put times 10 to the minus 6 to turn it to coulombs. That's what that prefix means. So coulombs gets us the right unit on there. You need to have, for using Coulomb's law, or for using these things, the SI unit is coulombs for charge, so we want it in coulombs. Okay, and then our answer, E, will be in newtons per coulombs, because you'll divide, you'll have this, you'll solve for this, and it'll be in newtons per coulomb. So anyway, so this is going to be, I'm going to put this as 35.6 times 10 to the minus 6 E times E. Because all we did is represent this. Okay, this is FE. So instead of FE, I'm writing the expression EQ. Okay, now let's do the other tried and true one we know. It's mass times gravity, FG. And our mass is 0.00510 kilograms. You got to turn this to kilograms, so this is in grams. Divide by 1,000, so 3 to the right. 1, 2, 3. Huh? Yes. And so it's that mass times 9.81. Okay, we can get a number for that, and my number is 0.0050031 newtons. So I'm going to write this as 0.0050031. Okay. Okay, now we have this force right here. But I'm going to redraw this. Okay. Let's do it over here so we can. This is F T Y. This is F T X. So now let's split this. Well, how do you split this? Well, we know this angle. That's 19 degrees for me.
Hey, Daddy, are you there?
I'm there, buddy. Hi, I can hear you.
I first put your phone call on.
Okay, I got my phone call right here.
Your phone is 12:35, and your first and your time is time, and the time and the clock is pointing to 5, so it's time to make cupcakes tomorrow.
Okay, can you make me some food in your little shop?
Okay.
Okay.
Bye.
Bye.
I need to put this on my
He is cute as can be. All right, now, so this is FTY and FTX. So we want to get those in terms of this. So we've done this many, many times. So we're going to represent this with these two, but it's, so this is sine. Oh, there's not, Luke? All right, sine of 19 equals opposite, which is FTX all over FT. So when we solve this, I'm just solving for FTX. And we're going to multiply FT over here, and I'm going to take the sine of 19. Oh, sounds good. Make me an ice cream cone then. And we're going to get a decimal equivalent of sine of 19. And the sine of 19 is, there we go. So it's 0.3265. Where's my ice cream cone? Times FT. So that's equivalent to this. So we're going to rewrite this as 0.3265 FT. So by getting it in terms of the same variable, it eliminates one variable from the whole system, which is nice. So by the same thing, cosine of 19 will be this adjacent here. So its cosine of 19 is FTY over FT. Now we multiply the cosine of 19, I'm going to approximate that. And approximating that gives me 0.9455. Your calculator better be in degrees, not radians, if you're using 19 degrees. So that's critical. And this is FTY. So we're going to represent this now with that. So this is 0.9455 FT times FT. So now, this thing is in static equilibrium. Static equilibrium means that the sum of the x direction forces and the sum of the y direction forces, they're equal to each other. They counteract each other, so it's a non-accelerating object, and it's also static, so not moving at all. So that's an extra little piece of information from that. So we're going to set the x, use the equilibrium expression for the x directions, which is F E equals FTX. So that's this equals this. And so we're going to have 35.6 times 10 to the minus 6 F, or E, sorry, E equals
should have been about 4 minutes 30 seconds.
0.3265 FT. Oh, two variables. So let's just leave that alone. So this is this expression. Let's do the same expression for the y direction. So it's 0.9455 FT. Check. Equals. Check. And put a division between the two sections there, a dividing line there, equals 0.005031. Oh, we can solve this. So we just divide and we get an FT equals to 0.005291 newtons. Now we can plug in over here. Minus 6 times E equals 0.3265 times what we just got for FT, which is 0.00529113, and multiply those two and then divide by that. Make sure to put parentheses around this because you got to get that. This is in scientific notation, so you got to containerize that value there. Oh, my ice cream was great. Can I have another scoop?
Is this vanilla?
Yeah, and so then when I divide those,
I found the vanilla.
48.38, and our units are newtons divided by coulomb, so newtons per coulomb. Oops, we're running.
Is this vanilla?
There we go. And that's our answer, and if you look over here, that's our answer. So there we go. So, all right, that was not nearly as bad. Kind of had some got sidetracked a little bit, but